And so first of all, I'm very sorry I cannot be there in person. I would have preferred to present my work in person in Boston now. But yeah, unfortunately, it's not possible. And so at this point, also a huge thanks to the organizers for giving me the opportunity to still give my talk virtually now. So during my presentation, I will jump on this very recent hype, which is increasing all the time, and talk about transformer models. And I will show you how we can use them to simulate or find ground states of quantum many-body systems, which corresponds to variational Monte Carlo methods. And so the reason why we are looking into transformer models now is that we have seen recently that they are extremely powerful. So especially in tasks of like language processing, that's where we have all seen them a lot. And I'm pretty sure every one of you has seen a lot of these applications as well. So just to name a few examples, the DeepL translator, which is based on a transformer, is a really impressive tool you can access online, where you can translate text from pretty much any language into any other language. Another example is Grammarly, which is extremely useful, or I personally find it extremely useful, which can basically interpret text and find mistakes or typos in text, also grammar mistakes, and provide suggestions how to improve your writing skills. And of course, the very famous example of ChatGPT, which is also just based on a transformer model, where you really have a virtual engine you can interact with, and you can ask it questions. And in many cases, the answers you get are really useful. What is really impressive about all these models is that they can all deal with extremely large texts, like long texts. And this is basically because these transformer models are really good at capturing correlations in sequences, and even in long sequences, and even correlations that are over large distances within this sequence of text. And so this is the point where transformer models outperformed all previous sequential neural network models and gave us this extreme power that we have now. Another example where transformers are currently applied is image processing or image generation. One famous example is Dolly, where we can just ask the engine to draw us a picture, so we can really describe it in words, and what we get out is some really fancy picture, which looks pretty good and pretty realistic, even though it never existed. You can also ask it to extend a picture, so we can send it, or we can give it some as an input some image, and it can draw an image around this small image, which again looks really realistic, even though no one has ever drawn these images. We can also ask it to just modify images and add elements to an existing image. And so again, this is really impressive. And again, it works so well with these transformers because transformers are good at capturing long-range correlations in a sequence. So here in this case, our sequence would be the sequence of pixels. And you can imagine that two pixels, like at the lower left and at the top right, are pretty far away from each other in the sequence of pixels, but they can still be strongly correlated. And this is where transformer models outperform previous sequential neural network models. And so these correlations are not only important when we talk about text generation or image generation, but apparently they are also extremely important when we look at quantum many-body physics. And so with quantum many-body physics, I'm always referring to just systems of qubits. And again, if we have a system of qubits, then we have strong correlations between these qubits, and they can be of long range. And therefore, if we want to model these qubit systems, it's very important that we capture all these correlations and even these strong long-range correlations. And so based on this relation, people started to use transformer models in this field of quantum many-body physics for several applications. And all these works came out in the last year, most of them actually within this year, so in the last couple of months. And so in these examples here, people used transformer models for quantum state tomography. So basically reconstructing quantum states numerically from a given set of measurements, for example, experimental measurements, which work really well. Another example here on the right is where people used it as Hamiltonian learning models. So basically, they were able to just from a given amount of measurements to determine parameters in the Hamiltonian describing the system from which the measurements were taken. And they also showed that these models can generalize really well. So in these plots here, you can see they trained a transformer just in the central part. And then they used it to produce or generate data outside of this regime where the transformer model was trained on. And it still works really well and yeah, shows really remarkable results. Another application, which is the one I will talk a bit more about today, is variational Monte Carlo. And variational Monte Carlo basically means we are given some Hamiltonian of some qubit system, and we want to find the ground state, so the state of minimal energy. Yeah, we want to find a numerical representation of this ground state. And here we can use transformer models. People have done it and have shown that these transformer models, again, outperform these neural network models we were using before. And so together with my student, or former student, Czischek, oh, sorry, there's a slide missing, I think. Oh no, okay, sorry. So let me quickly introduce a bit more what kind of qubit systems we are looking at. So generally, all these people look at different qubit systems. There are different ways how you can realize qubits. I personally focus today on one specific kind of qubit systems, which are Rydberg atom arrays. So this is just one way to experimentally realize a system of qubits. Rydberg atoms are just neutral atoms, which can be prepared in two different states. So either in the ground state or in a highly excited state, or what we call the Rydberg state. We then arrange these atoms on lattices. So for example, on this lattice, two-dimensional here. And then we can get an idea about the state of the system of qubits via projective measurements, where we can basically read out whether each qubit is in the ground or in the Rydberg state. The system is then described by what we call the Rydberg Hamiltonian, which consists of three terms. So we have two terms which are generated by an external laser driving, and they affect each qubit individually. And so one of them, this first term, basically generates a Rabi oscillation between the ground and the excited state with frequency omega. And the second term detunes our excited energy level. Okay, so it basically shifts this excited state up and down in terms of energy. Then we also have this third term, which is now an interaction term between all atoms. So we have all-to-all interactions. And the way these interactions work, you can imagine it if we look at just a subset of such atoms, and we assume that one of these atoms is in the excited state, then we said, okay, this is a highly excited state, meaning that the electron is on a sphere with a very large radius. And then you see that this sphere actually comes pretty close to all the neighboring atoms, and therefore generates van der Waals interactions with the neighboring atoms. And basically the best way to describe these interactions, or this interaction term, is in terms of the so-called Rydberg blockade. So we can kind of define a radius, and within this radius around an excited atom, any other excitation would be penalized. So this is illustrated here on the left. So we have one atom in the excited state, and then in red we have the sphere with the Rydberg radius, and then any other excitation within the sphere would be penalized, which is why all the other atoms are in the ground state here. The reason why people start looking into these Rydberg atom arrays is that from theoretical or numerical studies, they have found that if we tune these different parameters in the Hamiltonian, then we can prepare the system in a huge variety of different phases of matter, which are separated by different kinds of quantum phase transitions. And so there's a huge playground for theoreticians to explore all these phases and all these phase transitions. So there's still a lot to find out about these systems just theoretically. Beyond the theoretical studies, these systems have also been studied experimentally. And this is also really impressive because experimentally, people are really able to accurately prepare these systems. So they can accurately arrange these atoms on different kinds of lattices in 2D, also in 3D. And just by tuning the parameters of the Hamiltonian, they can actually prepare the states in these different phases that were predicted theoretically. And so this very well-controlled behavior of these Rydberg atom arrays makes them very promising candidates for high-quality quantum computation and also quantum simulation. Another nice thing that is especially interesting for us today is that the Rydberg Hamiltonian is stochastic, which basically means its Hamiltonian has a form such that the ground states are always positive and real valued. So if we want to find a numerical or a classical representation of the ground state, we do not need to care about any complex phases because they are all real valued. And so the only thing we need to care about is basically the squared wave function amplitude, which covers all the information about our ground states. And this makes things much easier for us because if we can just deal with real numbers, it's much easier than if we need to worry about complex phases. Okay, so this is the qubit system that we want to look at. And now I said, okay, we want to use the transformer and find a numerical representation of the ground states of these Rydberg atom arrays. And so the basic question is, how do we do this? Like, how can we approximately describe qubit systems? First of all, why do we need to approximately describe them? Well, the reason for this is basically the so-called curse of dimensionality. So if we look at qubit systems, we look at a single qubit, then we can find it in two states. We can define the Hilbert space, which is basically the space consisting of all possible states of our qubit system. Okay, so for a single qubit, it has 2 entries. For 2 qubits, we already have 4 possible combinations of each qubit being in the up or in the down state, or 0 or 1 state. So we already have dimension 4 of our Hilbert space. And then you can imagine if we scale up our system and we have n qubits, then our Hilbert space scales exponentially with the system size. So we have 2 to the n states. And since we are in quantum mechanics, they all exist in superposition. So if we want to describe the system exactly, then we would need to take all these 2 to the n states into account, which we cannot do with our conventional computers. And so this is why we need to find approximative ways to describe these qubit systems. And one very promising approach is to focus on a subset of states. And here we can introduce what we call the physical states. And these are basically the states that describe the dominant behavior of our qubit system. Okay, so you can imagine that if we have a superposition of exponentially many states, then usually, and it is indeed the case that, especially for the states that we are usually interested in, that only a small subset of all these exponentially many states really contributes significantly to describing a given ground state. And so what we can do is we focus on these physical states, we neglect everything else that does not really just slightly contributes to the state that we want to model. And so now we have shifted our problem from solving this exponentially scaling problem of modeling exponentially many states to finding the subset of physical states. Okay, so once we have found the subset of physical states, we are good. We can just approximate our system by looking only at the physical states, but the task is still, how do we find the subset of physical states? And this we can do by looking at what we saw earlier, the squared wave function amplitude. So the squared wave function amplitude basically gives us a probability distribution underlying all these possible configurations of our qubits, so all the possible basis states. And since it is a probability distribution, it directly tells us how much each state contributes to the superposition state that we want to model. Okay, and so basically our numerical approach, or the process that we choose now, is we need to find a numerical expression for these squared wave function amplitudes. And once we have a numerical expression, we can sample these physical states from it because it is a probability distribution. And if we have a sample of physical states, we have an efficient approximation of our qubit state. And so sampling from a given probability distribution is something that our computers can do very well. So we know already pretty much how we can do this. So the main point that we need to address now is how we can find a numerical and especially efficient expression for these squared wave function amplitudes, or for the probability distributions underlying all our basis states of our qubit system. And yeah, this is where we use the transformers and perform variational Monte Carlo. And so one way to find a numerical expression of these squared wave function amplitudes, which has been explored recently quite a lot, is to use artificial neural networks, specifically generative artificial neural networks, which are basically made for encoding a probability distribution and allowing us to efficiently draw samples from this distribution. And so since transformers are nothing else than really strong and powerful generative artificial neural network models, my student, former student Kyle Sprague, and I thought about using these transformer models to approximatively describe these qubit systems. And so here we talk about variational Monte Carlo. So basically, we now want to take our Rydberg Hamiltonian that I introduced earlier, and we want to find an efficient approximative representation of the ground state of this Hamiltonian. So we want to find the state of the minimum energy. And of course, people have done this earlier. A very promising approach is to use recurrent neural networks as a wave function ansatz, so as a model to encode this squared wave function amplitude. And these perform very well, but people have also found out that they are limited if we have long-range correlations in our system. And so because these long-range correlations are the limitation in recurrent neural networks, and we learned earlier that transformers are much better than at capturing such long-range correlations, we would expect that transformers can do better just because this attention mechanism underlying or as the basic element of the transformer can describe correlations much better. And so before I show you how they perform and before I compare the transformer with the recurrent neural network, let me quickly summarize how we use recurrent neural networks to represent such quantum states and to find these ground states of a given Hamiltonian. And we do this by basically defining a sequence of qubits. So I assume that everyone is pretty much familiar with recurrent neural networks. So we have these RNN cells, which have a nonlinear structure inside them. So basically they have a number of hidden units connected by variation parameters that we can tune when we train our network. And then we apply these recurrent neural network cells to a sequence of input data where the weights are always shared. So it's always exactly the same cell. And we send in iteratively one input element after the other. We also propagate the configuration of the hidden units or the state of the hidden units. And by propagating this state, we generate a memory effect. So basically, we are now able to capture correlations between elements within the sequence because we kind of encode the information about previous sequence elements in this hidden state and we propagate it over the sequence. And so if we now want to use this for our qubit systems, especially for our two-dimensional qubit systems, we need to find some sequence, or we need to define a sequence of qubits. And this we do by just snaking through our two-dimensional lattice here along these green arrows. And then what we use as an input is just the state of a single qubit. We send it through the RNN cell. Then at the end, we apply a softmax function. So we turn the output of the RNN cell into a probability distribution underlying two possible states, where we define one to be the 0 state and the other one to be the 1 state of our next qubit in the sequence. And then from this, we sample the next qubit or the state of the next qubit in our sequence. And then we autoregressively just use this sample that we have just drawn as the next input in the sequence and so on. And so this way we determine the state for all the qubits in our system. Now I told you we have this memory effect by propagating the hidden neurons. And due to this, the probability distribution that we sample from is a probability for the state of the next qubit in our sequence conditioned on the state of all previous qubits in our sequence. Okay, so here we always sample from these conditional probabilities, which now gives us the possibility to encode correlations between the different qubits in our system. And so now what we can do is we can take the product over all these conditional probabilities, which gives us a probability distribution underlying one specific qubit configuration, or basically one specific configuration of the entire sequence. And we can just interpret this as a squared wave function amplitude. And now what we need to do is we need to train our network such that this encoded squared wave function amplitude approximates the amplitude of our target quantum state, or in our case, of our ground state of the Hamiltonian. And so the way we train the network now is we evaluate the energy expectation value, which is basically the expectation value of the Hamiltonian operator. And we can do this efficiently by just drawing samples from our recurrent neural network. So we just generate different qubit configurations. We read them out here, and we use them to evaluate the energy expectation value. And then we train the network by just minimizing this energy expectation value, which in the end should have converged to the ground state representation. Okay, so any sample that we draw from our recurrent neural network basically corresponds to one projective measurement. So it gives us one state for each qubit in the sequence. And then we use these measurements to evaluate and minimize the energy expectation value. So this is how it is done with recurrent neural networks. Now we wanted to apply transformer models to do exactly the same thing. And luckily, transformer models also work pretty much exactly the same way. So we still have this autoregressive behavior. We define a sequence of qubits. We send in the state of each qubit one after the other. And we, as an output, we get this conditional probability distribution. We sample the state of the next qubit in the sequence, use it as an input, and so on. And so with this, we again just get the same output as with the recurrent neural networks. The only big difference is that we do not have any recurrency here. But as you probably all learned about the transformer models, they are based on this self-attention layer, which now is a bit different. So we do not encode all the information about previous elements in the sequence into this hidden state, but rather we have the ability to directly have weighted connections to previous elements in the sequence. And so this way, it's much easier to encode or capture correlations between elements in the sequence, no matter how far apart from each other they are. And that's basically the reason why transformers are so powerful in capturing long-range correlations, just because this attention layer gives us the possibility to encode direct or weighted correlations or connections to all previous elements in the sequence. Just for those of you who are familiar with transformers, we are using just the basic vanilla transformer. So the model that was introduced in the initial Attention is All You Need paper. So we did not modify the structure here. We just used it as it was provided. And then again, we can do the same thing as with the recurrent neural network. So we can take the product over all these conditional probabilities that we get as an output. With this, we get an expression for the probability distribution encoded in our transformer model. And we can train the model to approximate the squared wave function amplitude of our target state, or in our case, of our ground state. So we again draw samples, evaluate energy expectation values, and minimize the energy expectation value when we train our network. Okay, so let's take a look at how all this performs. So let's compare the performance of recurrent neural networks and the transformer when representing or finding this ground state representation of our Rydberg system. So we still look at a 2x2 or 2x2 Rydberg system. We have 8x8 atoms or 16x16 atoms on the left and on the right. And we just fix the parameters in the Hamiltonian to some values. I think they drive us pretty close to one of these phase transitions between the disordered phase and the striated phase. So we are pretty much in the critical regime here. And then we train our networks. And so we evaluate these energy expectation values. And what we plot on the left here is the difference of the energy expectation value that we get out of the neural network during training and what we call HQMC. So this is an energy that we evaluated with a quantum Monte Carlo method. So just a numerical method from which we know that it pretty accurately describes our Rydberg system. So we can benchmark our model by just looking at the difference between these two energies and assuming that our quantum Monte Carlo energies are pretty close to the exact energies. And now you see this energy difference as a function of the training iterations. And what we find is that they all converge pretty well. So we get pretty small energy differences for the transformer and for the recurrent neural network. Apparently, if we go to larger systems, like 16x16 atoms, the RNN does not perform that well anymore, while the transformer still performs extremely well. What is also really nice is that the transformer converges much faster than the RNN. So overall, we definitely find that transformers outperform these RNNs here because they converge faster and they converge closer to the exact energies. But of course, all these benefits come at a cost, and we can see the cost immediately if we just take a look at the computational runtimes. So we see that our RNN took 1.5 hours or 16 hours for the different system sizes. Our transformer model took much longer. For 16x16 atoms, we actually hit the limit of almost a week. We can only run jobs for a week on our cluster. So this shows us we cannot really go to larger system sizes with the computational resources we are given here. And so this is a main issue. So the transformer is really powerful, but it's also extremely expensive. And so we cannot really use it in this case. But of course, there has to be something to deal with this issue. And if we think about this example earlier, where I showed you that transformer models are used to generate or process images, then you can imagine that also images, they have a lot of pixels. So they have a huge sequence length. They have a lot of data that needs to be dealt with. And still transformer models are used efficiently for these images. And this is basically because people started to use this vision transformer here. And the idea here is that instead of having a sequence of single pixels, people just take a sequence of patches of the image and use these patches of the image as inputs to the transformer model. This significantly shortens this sequence length, and with this, of course, also the computation time. And now this is pretty similar to what we do with our qubit systems. So we can choose the same approach, and people have actually done this. So you see here on the right, so instead of really sending in qubit by qubit as an input to the transformer sequence, we can send in patches of qubits or groups of qubits at the same time. With this, reduce the sequence length and speed up our computations. We would also expect that with this approach, we can better capture local correlations, just because these local correlations are directly encoded in the probability that we get out from which we sample. This also gives us the opportunity to look at different lattice structures, just as a side note. So here, for example, Mohammed started to look at this Kagome lattice, where we do not have a square lattice, but just by looking at groups of qubits, he was able to convert it into a square lattice, and with this, use the just the sequence model that we had used before. Okay, and so inspired by all this, Kyle and I started to look into patch neural networks, and we are doing this, or you can do this not only for the transformer, but you can choose the same approach also for the recurrent neural network. And so what we did is we chose input patches of 2x2 atoms, which we sent into the RNN or the transformer cell. We process everything the same way as before, but then as an output, we get a probability distribution over all the possible configurations of the qubits in the patch. Okay, so now we have 16 elements in our 16 entries in our probability distribution. And from these, we sample the state of the next patch of 4 atoms. Okay, same process in the transformer model here. And so from this, we expect that we get this huge speedup because we divide the sequence length by 4. So we also expect that our computational runtime is divided approximately by 4. And as I mentioned, we expect that local correlations, which are directly encoded now in this output probability distribution, can be captured with higher accuracy. And so just quickly to show you how it performs. So here we look at these patches of 2x2 atoms. The upper 2 plots are the same data as before. And now down here, we have the patched approaches. Green is the RNN, red is the patch transformer. And we see that they converge much faster. Like both of them converge faster than if we do not patch our models. And nicely also, the RNN now can capture these 16 by 16 atom arrays. So this definitely makes everything better, so performance-wise. And if we look at the runtimes, it also significantly reduces the runtimes. Okay, so this is exactly what we expected. And so we get a significant speed up and higher accuracies just by using these 2x2 patches here. This looks so promising that we were wondering, okay, if 2x2 patches are really promising and really good, can we go larger? Because then we would reduce the computational runtime even further if we shorten sequence length further. And we would expect at least the same or even higher accuracies. And so the big question is, can we use larger patches here? The problem is, if we choose larger patches, then this means that our output probability distribution also grows. And this output probability distribution, again, this is the distribution over all possible states of the atom or the qubits in this patch. So the dimension of the output probability distribution scales exponentially with the patch size. And therefore, we cannot choose larger patches because we have to evaluate all these output probabilities exactly in order to sample from them. Okay, so here we were pretty limited. We could not just increase the patch size. But Kyle did not give up, and he came up with what we call the large patch transformer. And the idea here is that we use our transformer model just the same way as we had it before. And now we send in larger patches. So we send in patches of 4x4 atoms. But instead of just sampling the configuration of the next patch of 16 atoms, what Kyle did is he sent the output of the transformer model into a smaller RNN. And this RNN breaks down this large patch into 4 smaller 2x2 patches. And then it iteratively looks at each of the 2x2 patches at a time, right? So it samples the first patch, uses it autorecursively as an input, samples the second patch, uses it as an input, and so on. And so with this, we do not have this issue that we have to sample from this exponentially scaling probability distribution, but we can still use these large patches as an input. And now, of course, the setup we chose here is rather random. So we choose the transformer model as a base model, and then we have this submodel as an RNN. You could choose it the other way around. You could choose 2 transformers, 2 RNNs, and so on. So you can play around with this. We just thought that if we use the transformer at the bottom, we have our extremely powerful model, which can deal with these long-range correlations, which we apply to this large patch of atoms. or qubits. And then we have the very efficient RNN, which is still okay for smaller system sizes, which we use for when we break down the patches to 2x2 patches. Okay, so this is our large patch transformer model. And now let's see how it performs. So again, the upper plots are the same as before. Green and red down here are also the same data as we have seen earlier. So these are just the 2x2 patches. The new data is the purple one and the brown one, where we now use these large patch transformers with 4x4 or 8x8 patches as input to the transformer. And then the RNN always breaks down the large patches into 2x2 smaller patches. And what we see is that the performance, well, it converges a bit slower, but that's okay, because if we look at the runtimes, they have increased, they have decreased so much. So we are now so efficient and so fast that we do not care if we have to run more training iterations, because we just have the time to do that, okay? And looking at the accuracies, well, they are the same as before, pretty much. So what we have achieved now is we have found reasonable runtimes and high accuracies for finding these ground states of our Rydberg atom arrays. Okay, so overall, our large patch transformer gives us the possibility to efficiently look at these atom arrays. But now this suggests that we can go beyond these 16x16 atoms because we have so short runtimes and still high accuracies. So let's take a look at what happens if we go to bigger system sizes. And here the different colors are different system sizes. So we go from 12x12 up to 40x40 atoms, which is actually remarkably big. So this outperforms any numerical studies you can find outside now. And we look at the energy difference again. So this is after training the network. So we look at the final energy difference as a function of the patch size, or and patch size here is the input patch to our large patch transformer. Okay, and here we now not only focus on square patches, but we also look at rectangular patches within or to describe our Rydberg atom arrays. And well, you basically see that there's no big difference between squared or rectangular patches. They all perform pretty much the same. And you see that up to 8x8 patches, the accuracy is pretty good. So the energy difference is pretty small. And then our performance gets worse. And this is basically means that at some point, the input patch gets too large. We expect that this is because the RNN, which is on top of our transformer, still has a very limited expressivity. And at some point, our patches can get too large, so they are not captured that well by the RNN anymore. And at the same time, we have an increased amount of information that needs to be captured or reconstructed in our neural network. And so we kind of expect that at some point, our patches will get too large and our performance gets worse. But if we stick between or below patches of 8x8, then no matter which system size we look at, we always get really good accuracies, even below the uncertainty of our quantum Monte Carlo simulations. So we can definitely outperform our previously existing numerical methods. Just a quick look at the runtimes. So now we are looking at the computational runtime it takes for one training iteration in seconds as a function of the different patch sizes again. And we see that especially for smaller patch sizes, the runtimes decrease quite quickly. At some point, they saturate. And this is basically due to an implementation detail. So if you imagine we increase the patch sizes, then this means we need our memory requirements. So we kind of had to modify our implementation for larger patch sizes to stay within a decent amount of memory. Sorry. But overall, what we find is that if we choose patches around 8x8 qubits, then we can model enormous system sizes. Again, they outperform anything that you can find in the literature these days. And we still stay at pretty low computational costs. So these simulations are really still very efficient. And so this brings me to my summary. So I showed you that we are considering patches of atoms instead of single atoms when we reconstruct or represent our quantum states with these sequential models. We found that this leads us to higher accuracies and shorter computational runtimes. And we have shown or seen that the large patch transformer shows remarkable results beyond any state-of-the-art simulations by just combining this extremely powerful transformer model with the efficient RNN to break down our patch sizes. I have shown you all these examples for our Rydberg atom arrays. generally they can be applied to any kind of qubit systems. And just as a last note, the transform models that we chose here are still extremely small compared to what GPT or other language models are using. And so there's still a huge potential to increase these models, and with this get the opportunity to look at more complex qubit systems and even larger qubit systems. And so this is something we want to explore in the future. So let me finish with thanking my research team of students, the Apricot, who's presenting our very new and recent t-shirts, and also Kyle Sprague, who's not on the picture anymore because he already left. But yeah, he basically did all the work on this. So yeah, thanks a lot for your attention, and I'm happy to take any questions.
Very much for the presentation. We have a bunch of questions. All right.
Thanks for the very nice talk. So you said at the start that some of the Rydberg arrays are 3D systems as well. Have you looked into doing things with the 3D systems? And also another sort of technical question, how are the error bars on the previous plot defined?
Okay, so for the first question, so these 3D systems, they were realized experimentally. We have not looked into 3D systems yet, mainly because there's still so much to explore from the theory side just in the 2D systems. So we didn't go to 3D yet. Second question. Sorry. Oh no. Wait, please. No, you don't see my screen anymore. Just a second. Okay, there we are. So the error bars, right? So these were just just taken over multiple runs. So we were running training the networks multiple times. I forget how often, but yeah, it was multiple times, and then also averaged over several training iterations.
Okay, I think I have a quick question. This is kind of like maybe central to the problem you're trying to solve, so maybe this is something fundamental I didn't understand. But it seems like the reason why these making the patches bigger doesn't work out of the box is because you're increasing your essentially vocabulary size. And I'm not sure why that's different from just predicting this the state of every qubit. Isn't that still the same number of predictions you need to make, or?
Yeah, it's the same number of predictions, but the problem is that your output dimension of the network scales exponentially with the patch size, right? So like here now we have 16 possible states for this 2x2 patch. If we go to 4x4 patches, we would have 2 to the 16 possible states, and we would need to evaluate all these probabilities to then sample the next, or the configuration of the next 4x4 atom patch, right? So this is the limiting factor. But if we go to this RNN network, our network output, or the probabilities that we sample from, they are only defined on these 2x2 patches. So we basically break it down so that we only get an output of dimension 16 at every step. Okay, so it's in the end the same number of evaluations, but it's just more efficient because you don't need to take all of them into account at once.
So the main concern is like at evaluation time, essentially, not at training time. Is that correct?
Yeah, well, in the end, it's kind of both, because we need to evaluate, like we need to draw samples when we train the network. We evaluate the energy on this using the samples from the network. So also when we train it, we have to we have to sample from this probability distribution. So it's involved, yeah.
In training time, you could just do sort of like next token prediction without sampling, right? Or
no, because you you still need, like, in order to get the energy expectation value, you need the samples you need samples of qubit configurations.
Okay.
So it's not, so you're not training on data. You really just need these samples, evaluate the expectation value, and then based on this,
you just don't have that data at all.
Yeah, exactly. Yeah.
Yeah, I understand now. Thank you.
Shall I go ahead? Steph, I have a quick question for the comparison. Like, how does it compare in efficiency and accuracy? Like, if you compare it to like other models, like tensor networks or in other dimensions?
Oh, yeah, that's a really good question. So we didn't look at tensor networks here, mainly because it's 2D. and tensor networks are always a bit limited in 2D. Yeah, so I mean, the problem is with these variational approaches that you never know if you really converge to the ground state. While for tensor networks, you know what or how much of an error you're making, right? So you understand your inaccuracies, while here you never know this. So I would assume that you're probably less accurate if you compare it for 1D systems to tensor networks. But yeah, I have to admit that I didn't look into 1D systems yet.
Thanks, Stefanie. Could you talk a bit about the choice of sequence-based architectures as opposed to graph-based architectures? It would seem that you might want to, or naively, I would think you'd want to match the kind of geometry of the Hamiltonian to the geometry that you're processing information. Yet you seem to do pretty well, even though you're kind of doing this dot matrix printer style way of parsing the data. So can you talk about some of that?
I can try. So yeah, again, I have to admit that I did not look into any graph structures here. So I really just chose this sequence or the sequential structure just because it's convenient and it's efficient, it's easy to implement, and it still performs pretty well. What other people, so specifically Mohammed Hibat Allah did this in Toronto, they looked at 2D RNN. So basically they were passing the hidden unit configuration not only during the sequence, but more like according to the arrangement of atoms on the lattice, right? So you basically also pass the hidden unit configuration vertically, not just horizontally as we did it. This definitely makes things better. It makes the performance overall better, but it's computationally more expensive. So we just chose this sequential approach because it's computationally efficient.
Okay, thank you.
Thanks for an fascinating talk. I was wondering about my question, I think, is similar to the previous questions. I was wondering whether there's the fact that this works well, in spite of increasing the vocabulary size, might hint at some approximate factorization that holds in these systems.
Yeah, that's a really good question. I haven't thought about it actually. Yeah, that's a really interesting connection to look into. Yeah.
Thanks.
All right, let's thank our speaker once again.